Thanks to our early entrepreneurs in the robot field, ABB has meant a great deal for the development and growth of the industrial robots worldwide. For example, thanks to ABB, arc welding is one of the largest applications worldwide today. There are so many reasons for us to be proud of ABB's robot history. I am proud, and I would like you to feel the same. So let's look backwards and see how it all began. I'm standing here beside the first electrical robot in the world sold to the industry in 1974. One of the most important persons behind this innovative bestseller is standing right here beside me. That person will guide us back to the early days, and he's the father of the electrical robot, Mr. Björn Weichbrodt. Welcome, Björn.
Thank you, Jan.
Björn, can you tell us how it all began? What was it like when you entered the world of robotics?
Well, for me that was in 1971, and looking back to the start, the first robot, the first commercial robot in the world was developed by Joe Engelberger at Unimation in the United States, late 1950s. And that was an hydraulic machine, rather big. It was intended for machine applications. I believe the first task was to work with a grinding machine. It was a rather large unit. It could be programmed point-to-point, accuracy 1 to 10 millimeters. And I believe at that time when I started there were something like 3,000 robots in the world that we knew about.
So this was the situation of the industrial robot when ABB, formerly ASEA, entered the scene. So Björn, what was the main reason behind ASEA's involvement?
Well, I think Kurt Nicolin, who was our president at that time in the 60s and 70s, he saw the potential of robotics as a future potential business. He had himself a professional background as a production engineer. I think he made a general decision to see if we could not get the company into that robot development as a business.
Were there any other reasons?
Well, yes, I think you have to realize that at that time, now in the 60s, numerical control tools, machine tools, electronically driven, that had become a generally available product. And that was causing our manufacturing plants to become very efficient in each singular machine operation. But when you tied a number of the machine tools together, the transportation in between took time and the whole process became quite long. And there an industrial robot could make a big improvement. You could speed up production. That was what we were thinking about, speed up production by machine tools. And what we had, the Unimation robot, could do that for us. But if you look at an hydraulic robot, it is very big, it is rather clumsy, it is noisy, it requires a lot of electric power, and it's not a very clean device. So it has a lot of disadvantages that really are based in the hydraulic drives. And we realized that, and we didn't really like those robots at all, but they were the ones that could do the job in our manufacturing plant for us.
Did ASEA at the time have the right conditions to develop its own robot?
Yes, I think so, very much so. And you must understand that ASEA was already a major company in developing electrical systems. So we had very good resources to develop electrical systems generally, already making numerical controls for machine tools. We had a very good capacity in mechanical design, mechanical parts of a robot. We had also a very good experience in software development. And the fourth part of it, which is just as important, is that we were also really good at running machine shops. And this meant we had the production technology. This is knowledge of how should you use robots. So yes, I think we had a very good position for entering the market.
Björn, How and when did you fit into the picture?
It started in late in 1971, and at that time I wasn't actually in ASEA at all. I was working with General Electric in the United States, where I have moved about 6-7 years earlier. I was in charge of a development group that developed automation, and very interested in robotics, but the initiative really went the way that I visited with ASEA to see what was going on. I was interested in Sweden. We started to talk about robotics, and the result was that Kurt Nicolin, he offered me a job to develop a new robot system, and I accepted. That's how I got in.
Could you describe how this project was set up and when exactly this happened?
In 1972, in April, we made a formal decision to start development the robot program. At that time, in April 72, I had formed a vision of that we needed a project team that would be a complete team, if you will, not only have the development phase of mechanical, electrical, software systems, but also something about the production technology, and also think about what would the applications be and how should we market it. Kurt Nicolin said yes to that. We got a yes, and we got in permission to get 20 people together that we picked out from various areas of the company, representing all these areas. And we had a very strong goal to develop a first robot physically present to demonstrate from April in 72 until February in 1973. Because at that time, Marcus Wallenberg, our very big chairman of the company, had decided that that would be a good time to demonstrate the robot for share owners and some of the public. So that was the starting point.
I'm very interested to hear more about your design principles, how you choose between the different concepts. So let's discuss the manipulator. All robots at that time were of hydraulic or pneumatic types. So how come that you didn't choose one of the existing technologies?
The designs that were available at that time were hydraulics and some were pneumatic, with all the limitations that we have talked about already. And in addition to that, there would be good reason to try electrical systems of DC drive type or stepping motor type. And if you really, as I did, started to think about where is it that we could expect the future to develop best, I felt that if you're going to run a project to develop a new system, a new main system for the ASEA company, we're a company that is a big expert in electrical systems, some computer systems involved in that too, electrical power systems. That company is for sure going to develop that technology strongly in the future. And hydraulics was a little bit more of a sidetrack, I felt. So as we continued the development and we continued to try different areas, we did it with hydraulic systems, with pneumatic systems, with electrical systems, but all the time I had in my mind that I hope it's going to be possible to end it up with an electrical system.
What were the main alternatives to create the motion?
We had basically two types that could be functionally working well. Our first thought was a stepping motor. If you know, a stepping motor is a motor that takes a step for each pulse that it gets, but it does not have a feedback system, so you don't really know absolutely sure that the robot is at its right position. And then you have to have a lot of extra margin in terms of the power in the motor. So we didn't really like that after we had tested it. Instead, we selected a drive with DC motor, actually a DC motor with a resolver, because we felt that that's going to give us a quiet solution. ASEA is a good company as far as making DC motors. We could get very high accuracy, we could get low noise level, a lot of advantages that would serve the purpose of having a robot not just for materials handling but also for process applications. So we decided on the DC drive.
Another major choice of concept was the coordinate system. Cylindrical and polar type of robots already existed. Could you elaborate further, Björn, what your main choices were?
Yes, I certainly can, because that was an important question at that time. You know, there are many ways you could build a mechanical robot, and why build it in this way? If you think about the other alternatives, to have a polar type means you're going to have a telescopic arm that is going to expand its length, and that can create inaccuracies. To have a cylindrical, you're going to have an arm that goes up and down like this. So if you're going to move a small weight there, it'll be a big arm at the same time. This is a very compact solution. We call this the anthropomorphic, which means human-like. And if you see, this kind of design, and you compare it with my arm, you see it has basically the same kind of geometry. It is very lightweight. It is very stable, it's accurate, it has no sliding motion, and you can also put some mechanisms into the arm, and it becomes very well protected. So we liked it very much, and that's what we picked, and others have been designed later on, but basically according this principle.
What about the transmission issues for the different axes?
Okay, let's talk about this, and luckily we happen to have a robot here, so we can show you. 3 of these are harmonic drives. That is a main, very compact kind of transmission that can have a very big exchange ratio, and that was natural, and actually the only solution that we could have in the robot. For some of the axes. On the main axis for the arm here we use ball screws, and you see that solution here, very good possibilities also to avoid backlash, and it becomes a rather safe, dependable motion. And then of course this is not complete unless we add also our own invention in this, because we managed to invent and patent, in fact, this parallel link system. I'll show you by turning the robot here. That gives you on the inside here, not the chain or some kind of a band, but instead a steel link system, a little bit like a drawing board, where we were able to patent this area. And you can see how that provides the connection from down here where the motors are, up to this link, and further on into the wrist. As you know, this is a 2-axis wrist, and the 3-axis wasn't yet in the original design. But all those transmissions were quite modern at that time, and they still function very well. They have a very long life, very dependable, and they don't require much maintenance. So we feel that was a good solution. Still is.
Now we understand your criteria and solutions for the manipulator. Let's move over to the controller. What was the current technology at that time?
Okay, well, here was our controller that had a lot of new things, which I'll get to later on. But if you look at what was available on the market, I'd say we had 2 solutions that you could possibly compare with and see how they were. First one was Unimation, then this big materials handling robot. And that was a controller that was basically a sequential control that could go between a number of sequence points, just like you program a dishwasher or a washing machine. You go through a number of set steps. That meant you could program certain positions, but you had no possibility of programming the path in between. So the robot could go like this or like this, and you only had that point and the end point. that you had programmed. So that was a limitation for the materials handling robots, and we had much bigger ambitions than that. Second was one that a company in our neighboring country here, Tralfa Robot in Norway, was using for painting robots. And they had an entirely different approach. They had a robot that you actually moved in a teaching pattern. You moved the robot, which was hydraulic and balanced, so you created the spray paint path that you wanted to have. And while you moved it, you programmed that into a regular tape recorder that was in a controller in a special tape loop. So then you could recreate the path without any changes, but you could not modify it in any way without basic reprogramming. So that did not have any flexibility really in that sense. And we didn't really like either one of those two, so we had to create a third kind of a controller.
Based on the weaknesses of these two types, you decided to go for a completely new controller. Björn, could you please explain this further?
Sure. This, you could say simply, is the new controller. Doesn't look much different from the outside from others, not even from the inside, but it does have a specific, very new feature. We were very lucky in this development by having the possibility for the first time ever really started to use a microprocessor base. Earlier we had not had access to that, but just when we were working on this, Intel in the United States came out with their 8008 8-bit microprocessor. And as we looked at that, that seemed to us to be a possible computer-based system that we could expand into path control, into sensor input possibilities. So we decided to try that. And so this is one that housed the small microprocessor, which I actually went over myself to the United States in the late fall of 1972 and picked up from Intel in California. So we were very lucky, saying again, to find this new technology right at our doorstep, basically, at the time when we needed it. And that became then very expandable for 2 generations.
Let's now talk about the programming of the new electrically driven microprocessor controlled robot. What could you really do with this robot?
At that time we felt that we were in a good position. We could actually do a lot, especially compared to our competitors. We had 16 input possibilities for various signals. We could program speeds, location of points. We could have a controllable path between the points, including the speed. We could have a search operation, and we could accept some other inputs too. And that gave us a start for developing the first programs for arc welding, for example, or gluing operations. And that was quite a bit and gave us a very good position compared to the competitors we had. And of course, not the least important, we had a base for further development since we now had a computer technology in the controller.
It all seems very modest compared to today's world of high technology. But we must remember that at this time, thanks to you and your colleagues' innovative thinking, ASEA can really support the industry to grow their use of industrial robots in completely new areas like arc welding, gluing and polishing, which is, as we know, hazardous environments for the human being. The robots before your time were simply not accurate enough and were lacking the important path control. Isn't that so, Björn?
Well, thank you very much. We're very happy that we managed to contribute to some of the advancements in robotics. And it feels to me, as I look at the technical developments that are being done today, that even after 35 years, we still have a robot that is a design model for generally all the competition that is developing industrial robots today. And that makes us very happy, looking forward to further steps.
Thanks to you, everybody at ABB can be extremely proud of what you have achieved and that we have meant for the contribution to the robotics industry and the users of robotics worldwide. Thank you very much, Björn,
Okay.
the father of the
Thank you,
electrical
Dan.
robot.
Thank you.
Thank you.